friends. It's your guy, it's your dude, it's your man, the knick-knack, cardiac attack, patty whack, raptus, here to show you the way that we do SwiftUI code to wonder and amaze that doesn't take days. Find the repository link in the video description. You can also find a link to the next tutorial and the final project. Like, subscribe, and share with your friends. What we're building is the app that you see on the right. This is essentially a thumbnail grid. It solves all of the common UI and UX problems associated with trying to build custom layouts that download content over the internet. The focus of this tutorial is the UI itself. So we are going to simulate the web service calls. We're going to simulate them well using an offset and a count. The thumbnail downloads are also going to be simulated as separate tasks. Basically, this is built to work as enterprise quality code. And we're going to do the UI just about as efficiently as possible. You might notice a little bit of lag in the simulator, but I promise you that lag is not there on the device, going back as far as iPhone X or even earlier. So right off the bat, I of course wanted to make sure that we did support pull to refresh. We support this prefetch, so when you see these yellow cells, they don't yet have their data loaded. Once they turn light gray, they've got data loaded. When they turn dark gray, they're actively downloading their thumbnail. Once they turn to an image, they have downloaded their image in a simulated way. So we're also supporting this smart load scheme. So based on where you scroll, it's going to start pulling content there in terms of downloading the thumbs as well as the prefetch for the data. So you could potentially have huge gaps in your data. We don't right now, but that is certainly possible. We're going to support all the devices, iPhone, iPad, iPod, all sizes. For the thumbnails, we're going to also support this retry type behavior. And then, of course, rotation. Awesome. So by the end of today, you're going to wind up with this. And it's essentially a grid of numbers, but this isn't just a lazy VStack. This is a whole custom layout, and by the time we finish, we're going to need all of this cool custom stuff. So let's go ahead and start from absolutely scratch on, I'm using Xcode 13. This is going to work on later versions as well. And all that I've done is I've gone File, New Project, and I'm going to build an app. I'm going to call this Slick Thumbnail, and build it to my desktop. So we're going to use model view model architecture. Let's go ahead and create that triplet now. I'm going to build a new file, make sure it's a SwiftUI file, and I'm going to name this my page view. This is going to be the view. I'm going to make the second leg of the three-legged beast. This is going to be a file. This will be our view model. My page view model. Finally, the final leg of the beast, the model itself, again a Swift file. I'm going to make it my page model. So I'm going to start with the common pattern that you would use for model view model, and this is to make the model as a struct. My page model. Then the view model is almost always going to want SwiftUI, and it's almost always going to be a class. And it's almost always going to conform to observable object. Let's go ahead and give the view model a member instance of the model. So I'll say private let model equal my page model. Next, let's link it to the view. So in the view, let's go ahead and make an observed object for view model as a my page view model. We're going to run into a problem here that we're missing the parameter view model. A good idea is usually to link up the preview to some type of mock of your model. So let's follow this pattern and say static func mock my page view model. And I'm just going to go ahead and return a my page view model. And back on the view, let's go ahead and use this automatic error fixer. And we can now just say my page view model dot mock. Cool. Next, let's go ahead and link up my page view, and we'll just make that the root view. So we can delete content view at this point. I'm just going to move it to the trash. And I guess I'll move these files we just created to the top. But this takes us right down to the app level. So we're going to need a copy of our view model. And since we're just doing a chintzy little app, we can just add it right here to the app. My page view model equals my page view model. Content view is being killed off and replaced by my page view, and we just pass in my page view model. Let's make sure that we're loading the right thing just for our own sanity. So I'm going to change that default text on my page view into something more like my page. I'm going to target something like the iPhone 12 Pro Max, and I'm just going to run that and make sure it works. Alright, so we know we have my page view showing up. Okay, this is great. Now let's replace our body with the real body that we want. And I'm going to wrap everything with the geometry reader because eventually we're going to want to be detecting where those cells are in our scrolling content. So we're going to have an outer geometry reader and an inner geometry reader. So I'm going to call this container geometry in blah. We would love to use a scroll view for our custom grid, but unfortunately that doesn't support pull to refresh on the current version of iOS. So I'm going to use a list like a scroll view. Make private func list. This is going to take that container geometry as an argument, and that is a geometry proxy. This is going to be a little view builder, so make it say some view, and for now we'll just return a list. Let's go ahead and call it in our geometry reader content. And let's go ahead and get something else showing up on the screen as quickly as we can. So I'm just going to do a little for each and go from 0 to say 12. Index in. And we want a nice little rounded rectangle style thumbnail. Let's use a Z-stack for that. And I'm just going to give it an arbitrary size or frame of 100 by 100. We can keep the default alignment. I'm going to make the background be a shape of rounded rectangle with the corner radius of 12. I'm going to fill it in. I'm going to make the foreground color be orange. And then I'm going to give us a way to distinguish between cells. So I'm going to put a text inside of this cell that just simply shows our index. Then let's make it black and let's make it huge. So let's make the font be a system font of size 44. Let's see if that gives us something to look at. So I'm going to build and run again. Alright, cool. So we have a one-dimensional grid of thumbnail cells. We want to get to a nice 2D grid, but that's going to take some work. So let's go ahead and build what I'm going to refer to as a helper for our view model. And this is going to be something that defines the layout of our grid. I'm going to make a new Swift file and call it grid layout. I'll drag it to the top. I'm going to make this a class, grid layout. I'm going to go ahead and import SwiftUI. We're going to eventually want to talk to the UI. Then let's just define what we want from this immediately. We want a cells frame, which is going to be x, y, width, height, based on the cell's index. We also want the size of the whole grid of cells. We want the size of the entire content. I'll just call it grid. And that's about it for now. Eventually we'll want more. So for everything that gets plugged into UI, we want to send back a CG float. So let's go ahead and just make variables to hold these things and assume they're going to be computed eventually. So I'll say private set var width as a CG float, and private set var height as a CG float. This is the content grid entire width and height. Then we want this whole frame for the cell. And I'm going to give these initial values, and I'm going to give everything initial values because that's going to make us not need to implement a giant init function. I'm going to do something weird, and I'm going to already make an extension for grid layout. And this is going to be an extension that is only concerned with cell frame helpers. So we want x, y, width, and height. We're going to make each one a separate function. So I'm going to say func get x, and then it's going to be based on index as an integer, and that's going to return a CG float. And for now, I'll just make it return 0. I'm going to make similar helpers for y, width, and height. So I'm just going to do copy and paste and make them these 4 things. So this would already kind of let our view or views talk to this to get some information about how we want to lay it out. But we obviously need to compute that, and we're going to do something that seems a bit redundant or a bit reinventing the wheel perhaps, but in the end it's going to give us a much cleaner solution, and it's going to enrich our knowledge base so that we can do similar things again in the future. So I'm just going to define all of this. I'll call it cell grid layout parameters, and I'll just say let cell spacing h equal 9. It's going to be padding and spacing, so I'm going to do cell padding left. I'll make that 24, and then cell padding right. I'll also make 24. Then we need all the vertical stuff, so let cell spacing v. I'll also make that 9. Let cell padding top. I'll make that one 24. And then let cell padding bottom. I'm going to make this one 128 in case we want to add a advertisement at the bottom. To actually lay out the grid of cells, we certainly will want to know how many elements we need. So I'm going to kind of presumptively assume we have that, and I'm going to assume we're going to be able to set this possibly from the outside. So I'll say private var number of elements, and I'm just going to set this to 20 for now. And let's add another requirement to grid layout. We want the visible cells on the screen. So we want models to represent the visible cells on screen. And I'm just going to put in parentheses that these should be identifiable. So let's build that model. And this can be a super simple model. I'll just make a struct thumb grid cell model, and we're going to keep seeing index. So let's give it an index, but we want it to be identifiable. and we want that to be an int too. So identifiable, which means we need ID, and I'm gonna just make this mirror index, and I'm gonna move this all onto one line. This means return index. Then let's go ahead and add a little hook to do this task. So what we want is a func get all visible cell models, and that would return an array of thumb grid cell models. For now, let's just loop through our number of elements. So for, say, index in 0 to number of elements, we want to build one of these models. So let new model equal thumb grid cell model, and let's give it that index. So we want an array. I'm gonna make this a member var, and we'll keep reusing that same memory. So I'm gonna say private var all visible cell models equals an array of thumb grid cell models. And whenever we call get all visible cell models, I'm just going to remove everything in all visible cell models, but keeping capacity. So it won't need to keep reallocating that memory. Then I'll just go ahead and add that new model to all visible cell models via append. Make sure you don't use contents of append new model. And I'll just return all visible cell models. So let's try to get to the point where we can see it change. We have this grid layout, and it looks like we're kind of starting to try to do some stuff. Let's put a copy of it on our view model. So I'm just going to say let layout equal grid layout. And then on the view, on this list, we're doing this for each from 0 to 12. We want to do this for each over all of our visible cell models. So I'm going to say let layout equal view model dot layout, and then I'm going to say let all visible cell models equals layout dot get all visible cell models. Then we have more than one statement in our content, so we now have to say return list. But to iterate over all visible cell models, we really just have to replace the content of the for each with all visible cell models. This isn't going to be an index anymore, it's going to be a cell model. And here, this index can be cell model dot index. So we should be able to build and run now and see a change. Let's try it. Okay, awesome and double awesome. So it doesn't look like much changed, but you can see there's 20 cells now. That's coming from our number of elements that we hard fixed to 20. So these are our cell models now. So we're getting closer. Awesome, great. But how do we go into our 2D grid? How do we lay it out? How do we calculate the geometry? We're gonna need the size of the area that we want to lay that out in. And conveniently, some of those puzzle pieces are already coming together for us. So we just need to, before we get our visible cells, because visible might be impacted by the size of our frame, we want to register the size or the geometry of the container. So I'm going to say func register container, and this is going to take container geometry, and that is a geometry proxy. But to build our grid, we also really need the number of elements. So I'm gonna do something a little bit weird and just pass that here too. That's gonna be an int. So from the geometry, we really care mostly about the frame. So I'm gonna make another private var container frame. I'm gonna have that be a CG rect, and I'm gonna start it at 0 equals cgrect.0, just so we don't have to initialize it. So I'm gonna say now, did something change? If so, we want to re-lay out our grid. So we can get a frame from container geometry. So I'll say let new container frame equals container geometry dot frame in global. So if either one of these changed, I'll say if new container frame is not equal to our container frame, or the new number of elements is not equal to our number of elements, something changed. So we'll set our container frame equal to the new container frame. We'll set our number of elements equal to the new number of elements. And I'll go ahead and print this update. So I'll print new container frame. That'll be container frame new number of elements. This will be our number of elements. So when does this get called? It's going to get called from our view, because our geometry is on our view, and it's going to get called before we get all visible cells. But wait a minute, we're still missing number of elements. So let's decide where we want that to come from. And I think it makes the most sense to have the ground truth for that be in the model. So I'm just going to add a var total expected count as an integer, and I'll make that return just a random number for now, 118. So this is going to be how many elements we think the web service has. We don't need to do it this way, but this is a good way to do it to prevent jumps and skips. So we'll just, usually web services provide this anyway, but this is essentially how many data items we can get once we do all of our fetching. And really we need this to not fetch past the end of the list anyway, so it really becomes necessary to have the total expected count. However, we can't just access this because the model is a private member of the view model. And we're going to do this gatekeeping on purpose. So I'm going to make you have to talk to the view model to get that number. So I'm going to say func number of thumb cells returns an int. I'm just going to return model dot total expected count. So now we have a number, or at least we're hooked in with a way to have a number. So I'm going to go back to the view. And now before we get all our visible cells, let's do this registration. So we should have the pieces now. Layout.register container. Of course, we have the geometry. And for the number of elements, that's going to be view model dot number of thumb cells. So we should be able to build and run now and see that printout. Alright, so we got this printed out. New container frame, new number of elements. Notice that the top is not 0, it's 47. And the cool thing is when we rotate, that should update. And it does. Alright, great. Cool. Now let's go ahead and start boning out our grid. But first, let's reset that number of elements back to 0 because we're passing in the number of elements. Instead of computing this, printing this frame and number of elements, let's actually assume that we can lay out the grid here. So I'm going to make that into a new function. It can be private layout grid. So a grid essentially has a number of rows and a number of columns. So let's just assume we have those. Number of rows and private var number of calls. And we need to compute those. And we need to compute the number of columns first. I'm just going to put needs to be computed before. And I'm going to put number of rows. Because the number of rows is going to depend on the number of columns. So I'm going to go ahead and make a new extension to grid layout. And this one is going to be grid layout helpers. And I'm going to just put internal. This is internal stuff. So let's just have a function for number of rows. An integer. Let's have it return 0. And a function similarly for number of columns. Again, an integer. And up here in layout grid, let's just say, remember first we need columns. Number of columns equals number of calls. And number of rows equals number of rows. And I'll go ahead and print this. Laid out grid of blank by blank, and this is going to be the number of columns and the number of rows Let's do the harder one first, which is number of columns. So we can right away say that if we don't have any elements, e.g. the number of elements is less than or equal to 0, we have 0 columns. That's just kind of a mathematical fact. We want to base this on how big the cells should be for the screen size that we have. So just to make this stop complaining for a second, I'm going to say result equals 1 and then return result. Because if we have at least one element, our result's going to be at least 1. But let's backtrack for a second, and with these cell grid layout parameters, we're going to want something that we can use to compute the width and the height. And I think that we need to evenly lay out the cells horizontally so we consume the whole width of the screen. So a good way to compute the number of cells horizontally that we want is to have a maximum width. So I'm going to say let cell maximum width equal, just make it 100 for now. And then while we're doing width, we might as well do height. I'm just going to say cell height. And I'm just going to make that a constant number, and it's not like a maximum. This just will be the height of the cells, which means that one of our 4 puzzle pieces is done. So for the height, we can just return as a CG float cell height. Alright, so now that we have the maximum width, let's use the available width of the screen, or really it's the available width of the screen minus our paddings. So I'm going to say let available width equal our container frames width minus, it's cell padding left plus cell padding right. And this is going to be CG floats. We want to kind of compute the expected cell width as a CG float so that we don't end up returning the wrong result here. So let's essentially try out horizontal counts until the cells would be smaller than the maximum width. So since we're already starting with the result of 1, we can just start testing a horizontal count of 2. And I'm just going to loop. So I'm going to say while horizontal count is less than, say, 1024, just to give our loop a way to terminate. This is really an infinite loop, but it's just for a sanity check. So we need the amount of space between the cells for this horizontal count. So let's say let total space width equal horizontal count minus 1 times cell spacing h. And this again is going to be cast as a CG float. Then let's say let available width for cells equal available width minus total space width. So that's kind of essentially the container frame minus the padding and minus the spacing for this horizontal count. So now I can say let expected cell width equal that available width for cells divided by the horizontal count we're testing, but that as a CG float. And now we want to see if we're, again, smaller than the maximum width. So if expected cell width is less than, as a CG float, cell max width, something, otherwise something else. And let's fill in the something else, because really in the something else we want to try a bigger horizontal count, and we know that this is a safe horizontal count. Our cells are too big, or yes, too big, so we can keep shrinking them down. So I'm going to say result equals horizontal count here. So that doesn't ever let us terminate, but of course this is the terminate condition. Expected cell width is less than that maximum cell width. So that should pretty much do it for the number of columns. Luckily, number of rows is going to be a lot easier. So for the number of rows, it's essentially as simple as result equals the number of elements divided by the number of columns. However, you have to consider this case. If you had like xxx, xxx, x, that would be 7. So 7 divided by 3 would be 2 as an integer. So we need to take into consideration that spillover. And I'm just going to add this return result so the compiler quits complaining for a second. So to take that spillover into consideration, let's just say if number of elements modulus the number of columns is not equal to 0, result plus equals 1. And of course, this only works if number of columns is greater than 0, because otherwise we're dividing by 0. So otherwise, let's just return 0. And let's just go ahead and see if we get that printout. And we'll see if it makes sense too. Okay, that looks promising. So in this orientation, it tries to lay out a grid of 3 by 40. If we rotate it, it tries to lay out a grid of 7 by 17. I think those numbers look correct. Okay, great. Let's see what else we can compute now. To get the x values of the cells, we really want to know the width of the cells. And we're in a kind of interesting scenario where we're using integers for everything. So it could be that the widths of the cells in integers aren't all exactly the same number. So I'm going to make a list. I'm going to say private var cell width array and have that be an array of integers. Then similar to these other little computation helper functions, I'm going to make a func cell width array and this returns an array of integers. I'm going to go ahead and say var result equals an array of integers, and then return result. And then let's go ahead and fill this in. So in the same way that we computed these in layout grid, let's just say cell width array equals the computed cell width array. And we can print that too. I'm just going to print cell width array and just print that and get rid of this number of rows. Be good just to see it spit out a number. So let's go ahead and actually compute this. It's going to be pretty similar to our computation of the number of columns, where we take the container frame, subtract out the paddings and the spacings. So let's do it. So I'm going to do it a little bit differently by constantly subtracting out value from how much space we do have. And as we consume space, I'm going to keep subtracting it out, and then whatever's left, I'm going to evenly distribute. So I'm going to just say var total space equals, really as an int, container frame dot width. Then I'm going to say total space minus equals cell padding left, and total space minus equals cell padding right. Just to kind of illustrate the way that we're subtracting stuff out as we use it. I'm going to say subtract out the space between cells. So if the number of columns is greater than greater than 1, then there is space. So total space minus equals number of columns minus 1 times cell spacing h. And now we kind of have how much space can be occupied by those cells. So let's compute what the number would be if it was a floating number. It would be, let width of each cell equal total space divided by number of columns. But since this is integer math, this is really more of just a base width. So we might have some left over. Let's go ahead and we're going to have number of columns elements in the result array. So we can say for don't care in 0 to number of columns, result dot append base width, and then total space minus equals base width. Now there might be a little space left over. Evenly distribute that remaining space. So then while total space is greater than 0, we're again going to loop through, but this time I'll say for col index in 0 to the number of columns. Every time we loop, let's just say result col index plus equals 1 and total space minus equals 1. Now if we ran out, if total space is less than or equal to 0, we can just break out of this. So let's do it, let's run it and see what our widths come back as. Okay, that looks promising. We got 121, 121, and 120. So they must not have evenly fit on the screen. Let's rotate it. Yeah, we get 105, 105, and then all 104s. Okay, terrific. Now we have that width array populated. With it, we can compute the x value. We've always been able to compute the y value, but let's go ahead and do those both at once. So I'm going to say private var cell x array equals an array of integers, and then private var cell y array equals an array of integers. Then I'm going back down to our little helper extension. So I'm going to say func cell x array returns an array of integers, and I'll just give a default return var result equals an array of integers return result. I'm going to copy and paste this to make one for cell y array. Let's go ahead and prepare these to display. So I'm going to say cell x array equals compute the cell x array, and then cell y array equals compute the cell y array. So what should be in these things? We can compute these pretty easily, so I'm just going to make a little iterator variable and have it trace those positions based on the padding, spacing, and width. And for this one, the padding, spacing, and height. So I'll just say var cell x equals cell padding left, and then for index in 0 to, let's say, the number of columns, we want to advance that cell x. So cell x plus equals, we have the width array at that index, and I guess plus cell spacing h. Then we can just add to the result cell x every time and return it. The y is going to be even easier. We can just say var cell y equals cell padding top. And then we can go for don't care in 0 to number of rows. Cell y is going to advance by cell height plus cell spacing v. And the same thing, we're going to append it to the result.append cell y. Cool. So now we have the x array, the y array, and the width array populated. That just so happens to be what we're missing here. There's just one small problem. This index is like the index of the cell. It isn't its row column index. So we need to build some little helpers to help us convert real quick. So I'm going to make a function called column, which takes an index and returns the column index. And I'm just going to say if number of columns is greater than 0, return index modulus the number of columns, and by default return 0. Similarly, I'm going to make row, so func row, again with index is again returning an int. And this is again going to be based on the number of columns being greater than 0. In this case, it's divide, so return index divided by the number of columns. And again, the default is 0. Let's make the reverse of this too. So let's make func index taking as arguments row index and column index. And that'll be the cell index. So this is really just the number of columns times row index plus the column index. Alright, so now we can actually fill in all of these. So for the X, we're concerned with, of course, the column index. I'm going to do some stuff to make sure we're in bounds too. So I'm going to say var col index equals, and use that function column with our index. And I want to make sure that cell xarray has elements. This may seem crazy, but we kind of need to do this, especially when first booting up, in case we call these functions for some reason. Let's go ahead and constrain this for when we rotate too. So I'll say column index equals a minimum of column index and cell xarray.count -1, and then col index equals a maximum of col index and 0. And after we've clipped it, let's just go ahead and return, we already have it, cell xarray at column index. But remember, these are all CG float, so let's go ahead and cast it. Y is going to be very similar, so var row index equals row, again index, and again by default returning 0. And again, if cell yArray.count is greater than 0, we want to constrain this, so row index equals the minimum of row index, and cell yArrays count -1, and then row index equals a maximum of row index and 0. Then we return as a CG float cell yArray of row index. Width is going to be almost the same thing as X, so I'm going to copy X and paste it in width, but instead of cell xArray, it's cell width array. So I'm just going to replace those 3 instances with cell width array. And now we can compute our X, Y, width, and height. Terrific. Cool. Now we have almost everything we need to lay out our grid in terms of what grid layout needs to do. We got all the X, Y, width, and height for the cells. We're just missing the width and height of the entire content. So let's just fill that in real quick. So the width of the entire content, super easy. It's just the container frame's width. The height we need to compute. So the height is going to be essentially the number of rows times the cell height plus cell padding top plus cell padding bottom. But we need to take into account, add the space between each cell vertically. The height is, remember, a CG float, so that needs to be cast as a CG float. So for our space, let's just say if number of rows greater than 1, we can say height plus equals number of rows minus 1 times cell spacing v. And that can all be cast as a CG float. Cool. Alright, so to display our cells, we want to build a custom view builder. So let's build that. Let's build it as a SwiftUI view, and let's call it thumb grid. View builders always follow pretty much the same pattern. They have content, and that content is something like item, returning item view, where these are generics. So we're going to have a generic item and a generic item view. And we're going to pass in a list of items because we have a whole bunch of our grid cells. So this is going to be that whole grid. We don't need a preview because we're doing generics here. So I'm just going to say let list be a list of items or an array of items. And I want to for each over those and plop each one into its position. So for each in list, say item in. We can't for each though because item needs to conform to identifiable. So we can just say where item conforms to identifiable. That kind of gets us there. So can we just say content item? I don't think we can because we don't know what item view is. Essentially, item view has to be a view. But what we really want is to get our cell X and Y. So we need our layout in here. And what we want even more is a little helper function. And I'll just call it thumb, which takes an item as an argument and returns some view. And that is going to return the content. And here I'll call thumb with item as an argument. Now I want to get the X and Y, but what do we need? So if I say let X equal layout.getX, we need an index. So I'm going to comment that out. Identifiable doesn't have an index, it has an ID. So let's make up something, a protocol that we can use. So I'm going to say protocol thumb grid conforming and have that inherit from identifiable. And I'm just going to say this has to have an index, which has to be an int, and we need the get. Then I'm going to make item instead of conform to identifiable. I'll make it conform to thumb grid conforming. And now we can say layout.getX from item.index. And since we have that line, we need a return here now. So very similarly, I can get the Y, get Y from item.index. I'll go ahead and compress all this. And let's make this relatively simple. We'll just go ahead and offset this by X and Y. We're not talking about the width and the height yet, but we're talking about the X and the Y. Okay, awesome, cool. Let's level up our wizardry to 9,000. So we're passing in this list when we make a thumb grid. And we kind of have an inclination that we want that list to be of thumb grid cell model. So can we just make that, instead of identifiable, be thumb grid conforming? It happens to already be thumb grid conforming because it has an index and an ID. Awesome. So let's get to the point where we can see something already. So back on my page view, similar to how we made this function list, let's make another little function for grid. And I'm just going to copy this signature and paste it above and rename list to grid. And grid is just going to be a thumb grid. Ooh, but how do we get this list here? Well, we can just go ahead and do some of the same things we've already done, such as grab the layout and then grab all the visible cell models. And the list can actually be all visible cell models. The layout can be that layout. For content, we want essentially to define that here. So we can pretty much just take our Z stack and move it into the thumb grid's content. We're going to make a grid of those Z stacks. And for thumb grid, we do actually get cell model here, cell model in. And in our list, we're going to get a little bit tricky here. But first, let's make sure we can return that thumb grid, and the compiler will quit complaining. All right. So we're going to delete our for each from inside of our list, but we're needing essentially inner and outer geometry to eventually do clipping, and it's going to turn out that geometry reader positions stuff from the top left. So we want everything inside the list to be contained by a geometry reader. And here we're going to call this scroll content geometry in. And I think we want to pass scroll content geometry to grid too. So I'm going to just make it mandatory that we have scroll content geometry as a geometry proxy there. Little bit of a weird step, but alright. We no longer need all visible cell models here, and we can simply call from list our grid function now. And we have both the container geometry and the scroll content geometry, so that isn't a big deal. The geometry reader by default is going to size to fit this list. So we really need to dictate the size of the geometry reader, and to do that, we're going to use frame, and we have it all ready to go for us. We don't need alignment. So for width, I'm going to do layout dot width, and for the height, I'm just going to do layout dot height. So that's essentially going to build a scroll content inside of our list. We don't even need this grid. We would be able to scroll up and down in something blank. Alright, so the thing we're still missing is the width and the height for the cell. So these are going to be computed using layout.getWidth, and our index is just cellModel.index. And for the height, it's going to be layout.getHeight. And it's going to be cellModel.index. And it's going to turn out that we need this height not to be controlled by grid layout, or thumb grid rather. So it seems a little bit weird, but we're going to need to do it this way. So let's go ahead and build. We should now have a grid. Amazing. So after all of our computations, we see that they do actually produce this grid. Now what about all this weird padding? Let's go ahead and fix that. That's list's fault. I'm gonna go ahead and make the style into list style.plain, and I'm going to style up this geometry reader too by saying list row insets is equal to a blank set of edge insets, at that list row separator has no visibility. And that's going to be it. We got it. So our grid is complete. Pat yourself on the back. Remember to like, subscribe, and check out the link to the next tutorial in the video description. Thank you, and happy coding.